Proportionality is an important concept when studying the growth of plants and animals. Sometimes proportionality is also referred to as allometric relationships that we're going to see several examples of very soon. So first of all, what does proportional mean? We say that A is proportional to B if A is some multiple of B. So A is equal to some constant times B for a positive constant K. We call this K a proportionality constant. So oftentimes, we're not actually going to be able to set up a relationship with the constant ahead of time. We're going to keep it general and then using available data, solve for that constant K. Also, notice that while the constant has to be positive, it can be anything. It can be a fraction smaller than 1, or it can be a number bigger than 1. So for example, A being proportional to B might mean that A is 5 times bigger than B, or that A is half the size of B. In order for us to not have to write out A is proportional to B every single time, we introduce a notation of this sideways little fishy symbol here. So let's start with an example that refers to a physiological principle, and in particular that the strength of a muscle or a bone is proportional to its cross-sectional area. And the question is, if the athlete's muscle grew to double its radius, how much has the strength increased by? Does that mean that it's also doubled, or maybe it's quadrupled, or maybe it's increased by a factor of 10? This is what we're here after. So let's first of all take a look at the example and distill the information down to what we have. So first of all, it says that the strength is proportional to the cross-sectional area. So let's write that down. I have that strength is proportional to cross-sectional area. And now I have to figure out what is a cross-sectional area of a muscle or a bone. So simplest possible way to think about a muscle or a bone, think about a bone. It's probably, the picture that comes to mind is something akin of a cylinder, which is exactly what we're going to assume that it is. And then, of course, the defining characteristic of such a cylinder is going to be the radius. So how big it is in the radius here. So let's call it R, for example. Okay? So the question now is, the rest of the question actually makes a little bit more sense. If the muscle grew to double its radius, so if I had this radius and then the muscle grew to double the radius, so it increased to double the radius all the way around, how much has the strength increased by? One more note here on the fact that we're talking about cross-sectional area. Cross-sectional area means that I've sort of cut through the muscle and looked at what the actual picture sort of on the inside looked like. So it's kind of like maybe you can think about like cutting a salami and then looking at this picture here and realizing that this actually looks like a circle. So the cross-sectional area over here is going to be the area of the corresponding circle of radius r, which is pi r squared. So that means that the strength is proportional to pi r squared for the corresponding radius of the muscle. So now let's see what we have. Initial strength, so let's call it initial strength. This is not a stretch of imagination. Initial strength is proportional to the initial radius, so pi r squared. What about the new strength? So the athlete that we're talking about has clearly been practicing to the point where the new radius is actually doubled. So the new strength will be proportional to the new version of the same formula. So pi r new squared, right? So the new radius of the muscle squared. But we actually know more than that. We know that our new radius, r new, is actually double the initial radius because we are told that specific piece of information that the radius is doubled. So that means that I can replace this new radius with 2 times the old radius. Here's where you got to be really careful though, because in replacing it, I have to make sure that I place 2r exactly where the new radius is here and the whole thing gets affected by this square. So 2r all squared, okay? Don't make a mistake of saying that this is pi 2r squared. It's not. If I'm plugging 2r in for the radius here, the whole thing has to be squared. Okay, now let's open up the brackets here. So exponentiation rules, if you need to review them, take a look at the pre-calculus review package. The power will come down on both terms. So we will have pi times 2 squared, which is 4, times r squared. Now I'm going to move things around a little bit. I'm actually just going to move the 4, the constant, out to the front. And what do I have? 4 pi r squared. And now look here. My initial strength is pi r squared, and now I have it here. So I note that this portion of my new expression is actually corresponding to my initial strength. So overall, the initial strength was proportional to pi r squared. The new strength is now proportional to 4 times the original strength. And that is our answer. Once the muscle grew to double its radius, the strength has actually quadrupled. Okay, let's write that down and think a little bit more about the conclusion. Strength has quadrupled as radius doubled. The problem is with intuition here, it's easy to get caught up in the fact that if the radius got doubled, then the strength probably got doubled too. But the thing is, the strength is proportional to the square of the radius. So whatever factor the radius increases by, the strength will increase by the square of that factor. So if the radius doubled, the strength has quadrupled. If the radius tripled, the strength would increase by a factor of 9, and so on and so forth. So these are not in a linear relationship, so double, double, quadruple, quadruple. These are in a quadratic relationship, and we have to be more careful about plugging these types of things in. Let's take a look at the next example here, a little bit of archaeological inspiration. Estimating the mass of extinct animals is very hard because the artifacts of the extinct animals that we find in archaeological digs are bones. They have no muscle mass, skeleton alone, and we have no idea what the animal actually looked like. We have to derive it from the bones. And of course, depending on your imagination, this might produce a very different picture. For example, the saber-toothed tiger, whose skeleton was on the previous slide, might look very muscular, and more like a bear, or might be very similar to the present-day tiger, or, could be a cute little cat like this one, okay? So muscle mass doesn't necessarily depend on the skeleton. So how can we possibly derive the muscle mass of extinct animals? Well, the one thing that we can use is to study living carnivores, so in the same family of animals, and find the relationship between a part of their skeleton, in this case a skull length, and their body mass. So these are the types of relationships that are called allometric. They're power functions. Notice this is not an integer. They're proportional to each other, and they connect two things that we're interested in. Something about a skeleton and something about the mass. Hoping that the carnivores of the ancient times are not too different from the carnivores of approximately the same size living now. This is our best attempt at actually modeling the body mass of the extinct animals. So now the problem, of course, is we don't know this proportionality constant, and we're going to have to use other type of information to derive it. So first of all, we know that a gray wolf weighs 45 kilos and has a skull length of 275 millimeters. We are now, using this information, going to try to find the weight of a saber-toothed tiger whose fossils have skull length of 350 millimeters, and also find the skull length of it if it weighs 80 kilograms. So the same problem, but in two different directions. So let's start with the first part. First of all, let's rewrite our proportionality or allometric relationship here. So we have B is equal to k times x to power 3.13. What do I know that I can plug in order to figure out what k actually corresponds to? Well, I do have some information on the gray wolf, which is a living carnivore. So this actually comes from real data. I know that he weighs 45 kilos. So that is the body mass. And the skull length is 275. So this x is 275. So I can plug that in, 45 for b and 275 for x. And that will allow me to solve my equation directly for k. So I'm going to have 45 is equal to k times 275 to power 3.13. Okay, I can plug all of these into a calculator, and what I'm going to end up with is the value for k, which is going to be some number, but I'm actually going to keep it as a fraction in sort of calculator-ready form, so we can see exactly what it is and where it appears. So this is my value for k. Again, feel free to plug it into the calculator in order to actually figure this out. So this came from the gray wolf data. So now what about the saber-toothed tiger? For the saber-toothed tiger, I am looking at the exact same allometric relationship, except for now I also know the value for k. The body mass and the skull length are going to be different. So for the tiger, let me rewrite my equation here. K is known, so k is now 45 over 275, 3.13. Don't be scared of big ugly numbers, times x to power 3.13. So what do I know for the saber-toothed tiger? I know that the fossils have the skull length of 350. So my x, the skull length, is actually equal to 350. And the rest of the numbers on the right-hand side are already constants. So if I simply plug that in for x, I'll be able to figure out what the b value is directly. So my b is going to be 45 over 275 to the power of 3.13 times 350, which is its skull length, to the power of 3.13. This is for the saber-toothed tiger. If you plug it in, this should give you approximately 96 kilos for the saber-toothed tiger mass. Okay? There is a really nice feature of word problems, and that is the fact that you can actually make sure that your answer has some sort of common sense. So a gray wolf, the skull length was 275 and the mass was 45. The saber-toothed tiger, the skull length was 350, so more than that of a gray wolf. Therefore, we expect that the mass is also going to be larger, and 96 kilos came up being larger than 45. Now, you're not going to make, there's only so much you can do in terms of common sense, but if this came out being like 16 or anything below 45, you'd know that something went a little bit wrong. Also, if this came out being like 960, you'd also know something went terribly wrong because their skull lengths weren't so far apart that their masses are going to be so vastly different. Now, for the second part, we're going to do the exact same approach where we start off with our relationship as given. So let's actually see. I can copy paste this one from right here. And then fit in the information that I'm given. Find the skull length, so x is unknown here, of a saber-toothed tiger of weight 80 kilos. So now that means that I'm plugging 80 in for the body, and I'm actually looking for this value of x. Okay, this is fairly straightforward, so I'm going to leave it for you to find what this x is, and then also, again, make sure that you compare the number you get to the numbers that you've already seen and ensure that it falls within some reasonable boundaries. Let's do more proportionality examples. First up, we're going to talk about blood circulation time, which is the average time needed for blood to reach a site in the body and come back. So a site means any site, but we can think about fixing a site. So let's say this is a mammal of a certain body type, and the site of the body, for example, can be the toes of this mammal. So the blood circulation time is the average amount of time that it takes for blood to go from the toes around the body and come back to the same exact spot. For mammals, which humans are part of, the blood circulation time is given by this formula, where M is the body mass, T is the average circulation time, and K is some kind of constant that depends on a particular actual mammal, because we obviously function quite differently than some other mammals out there, depending on their body composition and a variety of other factors. So first of all, let's sketch the graph of this function. Again, K is a constant, so what we're looking at is something that is proportional to the fourth root. If you don't know how to sketch a graph of something, the go-to method is to always simply plug in numbers. So you can plug in numbers for various values of M, which will be sort of your X value here, and get out different values for your Y coordinate, which is T, and then see what the graph looks like. The other method is to pull up Desmos and let computer graph it for you. So what we have on the left here are square root, fourth root, and 10th root. The square root function will be a sideways parabola that is only present for the positive values of x. So you see only half of a parabola. It's not a fully rotated parabola, because if it was a fully rotated both branches, this would no longer be the function, as it would not pass a vertical line test. So we get half of the rotated parabola as a result. If I am now to reveal the fourth root, you will notice that they intersect at 1, square root of 1 and fourth root of 1, and of course 10th root of 1 and so on will all intersect at the point 1, 1 if they come with no coefficients. And you notice here that we can again think about the power domination the exact same that we did before. The smaller power, the fourth power, dominates before the switch point at 1, and after the switch point, the higher power, or the square root, the 1/2, dominates into the infinity. And so we expect that if I now sketch an even smaller function, then at the beginning, near the origin, it will be higher than the two functions that are already there, but then after the switch point, it will be flatter than either one of them. So this is how they also interact with each other, but in general, the even root functions are all halfway sideways parabolas. So going back to our slides, let's just put in a quick sketch of the graph. Of course, notice that when I was drawing them, I did not put in any kind of value for the constant K here. So all I'm interested in is the general format of the function. No scales on the axes, just a qualitative picture. Okay, so again, a quick note here. All even root functions are going to be sideways parabolas. Sideways, maybe I should point out, half parabolas, because again, we actually want them to be functions and pass the vertical line test. Is the blood circulation faster in small or large animals? So remember that this M represents the body mass. So if the mass grows bigger, do we expect the circulation to be faster or slower? Well, as the mass grows bigger, we notice that this graph starts flattening out. In the beginning, it grows quite a bit, and then it starts going slower and slower and slower. So it looks like in large animals, the blood circulation time slows down. This also makes sense in practice, right? If you think about blood circulation in, let's say, an adult human and versus a blood circulation in a kid, the blood has less body to circulate through in a smaller mammal, and therefore it will circulate through faster in them. For part 2 of this question, this is very similar to the athlete and the muscle question from earlier on. If the body mass doubles, how does this affect the blood circulation time? So let's go through a similar approach as we did then. So what I have is my T, my blood circulation time. Let's say old is what we have so far. So in the beginning, we have K times fourth root of M. And our new blood circulation time is going to be the exact same thing, except for the mass has doubled, which means that now, instead of M, I am going to have 2M replacing it. So my new blood circulation time is going to be K, fourth root of 2M. And this is where it really helps to be comfortable with how roots or rational exponents actually work. So if you're not, go take a look at the pre-calculus review materials for how to work with roots of all kinds of powers and how to break them up over the product in particular. So here what we have is, because it's 2 times m, I can break up the fourth root over the 2 multiples. So what I'm going to have is k times fourth root of 2 times fourth root of m. Now remember that what we actually want to do is to compare the new blood circulation time to the old. So I'm actually going to try to look for these values inside my new expression. And I can, of course, see them appear here. So what I'm going to do is just reshuffle this a little bit. I'm going to flip the order of the last 2 items. So I'm going to have k fourth root of m. You know what? Actually, I'm going to put this second. And what I have, my other multiple here, was fourth root of 2. So this can come out as a coefficient in the beginning. And what I see now is that this portion is exactly my old time for the blood circulation. So this part corresponds to t old. And so overall, what I have now is fourth root of 2 times t old. So what is the fourth root of 2? It's some number. You can pull out a calculator or you can type it into Wolfram Alpha and you will see that fourth root of 2 is approximately 1.19. Okay, so what I have is it's 1.19 times t old. So as the body mass doubles, the blood circulation time acquires a multiple of 1.19. Now, this means, think about this. If I didn't have the 19 here, then I would have 1 times t old, which means that it's the same as just t old. So this 0.19 introduces the increase. So t new is actually 19% higher than t old. Okay, and that is our ultimate conclusion here. As body mass doubles, the blood circulation time goes up by 19%. Here's another example of proportionality and how we can use it to figure out the increase or decrease relationship between certain quantities. Poiseuille's law states that the resistance of the flow of a liquid through a tube, so for example, blood through the veins, is proportional to the length of that tube and inversely proportional to the 4th power of its diameter. Okay, quite a mouthful, but here's the formula, and let's work through it. So the resistance of the flow of a liquid, which here is R, is proportional, so here's my proportionality constant K, to the length of the tube, this L, and inversely proportional means it will appear in the denominator, hence the fraction here, to the 4th power of the diameter of that tube. Okay, so maybe let's label all of the variables that we have in this equation. So this is the resistance of the flow. K is my proportionality constant. I'm not going to label that. L is the length of the tube, or again, a blood vessel. And D is the diameter of that same blood vessel. So a standard question is, for example, as one grows old and acquires cholesterol in their veins, how much is the restriction of the blood flow through the veins affected by the acquirement of said cholesterol, right? So cholesterol, of course, like if you have your blood vein here, cholesterol builds up on the outside, therefore making the diameter of the blood vessel smaller and smaller. So this question investigates of how does the thickness of the buildup of the cholesterol actually decrease the blood flow through the vein? So let's say the diameter of the blood vessel gets reduced by 10%. It's very small decrease, right? Just 10% due to cholesterol buildup. What happens to the resistance? Okay, applying the exact same technique we had before. First, I'm going to say that my old resistance, R old, is going to be K times L divided by D to power 4. I can actually also just combine the K and the L on top of this fraction. Okay, so this is my old resistance with the diameter D as stated. What about my new one? So my new scenario is the diameter of the vessel got reduced by 10%. Okay, so here we have to interpret what does that mean first of all. Being reduced by 10% means that if I started with D as a diameter, it's now 90% of what it used to be because it got reduced by 10%. So instead of D, I now have 90% of D. Okay, and that is what we're going to do here. So let me make a side note here. So D becomes 0.9D, 90% of D because it got reduced by 10%. So I'm going to plug that in for D into my resistance formula. So what I have is KL divided by 0.9 D all to power 4. So this is where you have to be really careful. You're plugging in 0.9 D in for D for the entirety of D. A very common mistake that people make is instead what you're going to write down is KL over 0.9 D to the 4th. The reason this is wrong is because you didn't actually replace D with 0.9D. You introduced this 0.9 outside of it, right? The entirety of D has to be replaced by 0.9D so you don't lose these brackets, okay? So look at this very carefully and recognize that this is not the right thing to write down. Now, if I do have that, what am I going to acquire next? I can open up the brackets at the bottom, so I'm going to have KL divided by, and again, this is where it really helps to be familiar with how exponents work. The exponent 4 will come down on both of the factors here. So I'm going to have 0.9 to power 4 times D to power 4. Okay, I can rewrite this again, looking for this as a part of my new expression. And I can, of course, see it right here, right? This is my KL over D to the 4th. So I'm going to try to isolate this factor. So I have this 0.9 to power 4 on the bottom outside of it. So I'm going to split that apart. 1 over 0.9 to power 4 times KL over D to the 4th. And as before, now I can see that this is my old resistance as written right here. So I can replace that. I can also actually calculate this number as a number, right? 0.9 to power 4, I can plug that into my calculator, can have 1 over it. This number will turn out to be approximately 1.52. Okay, so this is approximately 1.52, and this expression is just my old resistance. So times R old. Okay, so what do I have here? The diameter got reduced by 10%. So the new diameter is 90% of the old diameter. And what I have is that the new resistance is 52% higher than the old resistance. 10% reduction in the diameter of a blood vessel, only 10% reduced the resistance by 52%. And that is why the cholesterol buildup is so dangerous. A small percentage of buildup, because it is raised to the power of 4th, will produce quite a large increase in the resistance. We're going to consider in quite a lot of detail how spherical cells work, and we're going to start with thinking of the proportionality as applied to the cell's surface area and volume. First of all, we're going to make one very specific simplifying assumption. The fact that we are considering spherical cells, so perfect little spheres. Our entire analysis will rely on that as an underlying assumption, which means that if we start talking about cells of any other kind of form or shape, our results from this analysis will no longer be valid and will have to be redone for a different shape. So for example, if you're talking about a cylindrical cell, then none of our results for the sphere will apply to the cylindrical cells. we will have to redo the entire problem all over again. For now, we're going to be working with a sphere. So being a sphere, the size can be characterized by the specific measurement and namely the radius, right? So let's say I have a perfect little sphere. This is not three-dimensional, I am fully aware, but let's pretend that this is a three-dimensional picture where the radius of the sphere is r. First of all, we are asked to consider the surface area and the volume and show that they are in fact proportional to some power of r. Now, these are some of the formulas that are going to come in handy. You don't have to memorize them by heart. They will always be available to you. The surface area of the sphere is 4 pi r squared, and the volume of the sphere is 4/3 pi r cubed. So by sort of the various different tools, we know that these formulas are true. And in fact, if you take Math 112 or Math 118, you will show using integration that this is in fact the volume of the sphere. Okay, let's take a look at the surface area first of all. We are asked to show that it's proportional to some power of r. Notice that 4, of course, is a constant, and pi, of course, is also a constant. Pi is some number, 3.14, and so on and so forth. Whatever it is, while it is infinite in its decimal places without no repeated patterns, it is in fact a constant. So what we have here is 4 pi is some constant number, which means that we can think of this as a proportionality constant k, and we notice that this implies that S is proportional with proportionality constant of 4 pi to r squared. So let's write that down. S is proportional to r squared. And let's actually make it more specific with proportionality constant that we actually know. So oftentimes we assume that proportionality constant is some unknown or we have to solve for it. Here we actually know the proportionality constant is 4 pi. Similarly for the volume, 4/3 is of course a constant and pi once again is a constant. So 4/3 pi altogether is in fact a constant value, which means that this is some kind of constant, let's say again, call it k or something. And we can see that now the volume is proportional to r cubed. Let's record that. Volume is proportional to r cubed. And again, in this case, we actually know that the proportionality constant is what is given to us, and namely 4/3 pi. Excellent. So we have that the surface area is proportional to the square of the radius, and the volume is proportional to the cube of the radius, which also makes sense if you start thinking about how normally we have units for these things. The surface area, being the area, is normally, for example, centimeters squared, whereas volume is something like centimeters cubed. What do we have for part 2 of this question? Assume that the simplest spherical cells are made up of mostly water. Argue that their mass is also proportional to some power of r. So first of all, we have to come up with the link between mass of a cell and some other kind of characteristic of it. So if you have taken physics or talked about this in biology, mass is actually equal to density of the material that the particular thing is made out of times volume. Now, volume is something that we already discussed in the previous part. So what about density? Well, we're told that cells are made up of mostly water. So if we know water density, we're assuming that this is going to be the density of the entire cell, and therefore the actual number is going to be a constant. So what we have so far then is mass is equal to some constant, again, call it k if you wish, times the volume, which means that mass is proportional to the volume. Let's record that. So mass, we have a letter for it. Mass is m. So let's say capital M is proportional to the volume. which is our capital V. But we have just shown that volume is proportional to R cubed. So we can create this kind of sequence or chain of proportionalities. Remember that every proportionality means that there is simply just a constant present in front. So the other way to write this down is this is some constant times the volume, and the volume itself is some other constant times R cubed. Combining the two constants together, we have that the mass is proportional with a new constant to R cubed. So with the density being held constant, mass is proportional to the cube of the radius. Let's see how this is going to become helpful in trying to analyze properties of a cell. And in particular, we're going to talk about what happens if a cell or a spherical object, let's say a small spherical object, gets wet. Think about this. If a cell, and again, maybe not a cell, let's say a spherical small object gets wet, it's covered by water on the outside, on its surface. So it is reasonable to assume that the mass of the water that covers a spherical object when it gets wet is proportional to the surface area of that cell, right? Again, the water actually covers the outside of the spherical object, so it makes sense that the water mass that covers it is proportional to that surface area. We are asked to find a value B such that the water mass is proportional to the cell mass to some power. Okay, so let's maybe denote what these things are. This is water mass that covers the object once it gets wet, and M is the object's mass itself. So what the first part of the question is asking is show that, first of all, these two things are proportional, and secondly, find the exponent of proportionality. Okay, so what do we have from the previous slide and from what we have here? We need to connect the cell mass to the water mass. So first of all, let's talk about the cell mass. From the slide before, we have that the mass of the cell, let's flip back to take a look at it, is proportional to its volume, which is then proportional to R cubed. So as an end result, we have that the mass is proportional to R cubed. Excellent. This is from example before. What do we know in terms of water mass that covers the cell when it gets wet? Well, we're told that we've reasoned out and decided that it is in fact sensible that the water mass is proportional to the surface area of the cell. Okay, so water mass, let's call it W, is proportional to the surface area of the cell. And from the previous slide, we've discussed what the surface area is proportional to, and that came out to be R squared. So the surface area itself is proportional to R squared. Now, what we actually want to do is to connect these two quantities. So it's kind of like solving two equations, except for instead of equality, we have the proportionality sign here. And what we can notice is this tells us about a connection between mass and R. And now we have a connection between water mass and R. So I can kind of solve, quote unquote, this equation for R and plug it in here. Okay, so what I'm going to do is I'm going to rewrite this proportionality for R. Again, remember that proportionality means that what we have is M is equal to some constant times R cubed, which means that I can take cube root of both sides. The constant is going to appear to the cubed root, under the cubed root, but the rest of the relationship will still hold. So this is still a constant, so I will keep my proportionality relationship. If I take cube root of both sides, on the left side, I'm going to have M to power 1/3 proportional, and on the right side, a cube root of R cubed is simply R. Now this is great news because then I can plug that in for the expression into R. So R is proportional to M to the power of 1/3, and here I have R squared. Okay, so what I have is, because I am substituting for r here. R is going to be replaced by m to power 1/3, but then I had r squared, so I am going to keep my square. Okay, so this relationship went into right here. And now simply opening up the exponents, when we raise a power to a power, they get multiplied 1/3 times 2 is actually m to power 2/3. So what I have is that the water mass through the chain of proportionalities and equalities is proportional to m to power 2/3. Okay, let's write down that conclusion. So therefore, what I have is that the water mass is proportional to the 2/3 power of the mass. Okay, the other way to write this down, once again, is by using the proportionality constant. So this is some k times n to power 2/3 for some constant of proportionality k greater than 0. So we were asked to find the exponent of proportionality, and that exponent is 2/3. Okay, now on to the second part of the question. We're asked to graph the ratio of W to M as a function of M. So let's take a look at what that would give us. So I am interested in the actual ratio. And let's write it down. W divided by M. So what I have for W is the relationship I just derived here. So W is actually equal to K times M to power 2/3. And I'm dividing by M. Now, this is M to power 1. Remember that we divide, the powers get subtracted. So I'm going to have M to the power of 2/3 minus 1. 2/3 minus 1 is negative 1/3. So overall, I have K times M to power negative 1/3. If you need to do it by hand, the subtraction of the exponents, make sure that you actually write them down and get the right answer. Okay, so my ratio of water weight to the mass of the object is equal to this. Okay, now let's actually sketch it to see what's going on. We can go to Desmos and take a look at what the graph would look like. So here I've sketched x. Desmos doesn't like names for variables other than x and y. So I've sketched x to power negative 1/3, and I have this graph. Notice, of course, that it appears on both sides, the negative and the positive, but if we're talking about x here representing m in our problem, it refers to the mass of the object of the cell, so it can only be positive. So really, we're only interested in the actual positive part of this graph. Let's paste it out onto our slide here. This is just my positive portion of the graph. Okay, so once again, I'm fully aware that it exists in the negative dimension as well, purely as a mathematical graph, but for our application, we are only interested in the positive values for m here. So what do we notice? First of all, let me label the axis. So this axis will be the axis for m. Is going to represent w over m. Okay, so what do we notice? We notice that as m gets bigger, the ratio of w over m gets smaller and smaller and smaller. So the water weight to the mass of the object gets smaller and smaller as a ratio. The bigger the body mass m, the less amount of water the object has to carry relative to its mass. But what happens for small values of m? Let's take a look at the graph for small values of m. You notice how it gets larger and larger and larger? So it means that if the object is really small, the amount of water it has to carry proportional to its weight, it's huge. So notice that it doesn't mean that an ant would carry more water on its body than an elephant. It would carry more water proportional to its own body weight. So for example, an ant might carry 100 times more its body weight, whereas the elephant will carry just 0.5 of its body weight. Proportionality means in relation to its own value. So if you're an ant and getting wet means that you will have to carry 100 times your own weight in water on your body. That, of course, means that getting wet as an ant is much more dangerous than getting wet as an elephant. As we have seen with the examples just now, it is important to be acquainted with the shapes of the power functions, fractional power functions, and negative power functions. So, here is our chance to classify what their overall qualitative properties are. I encourage you to pause the video and then go on Desmos and try to plug in different values, for example, for n in all of these 3 different functions. Pick even numbers, pick odd numbers, stick to the integers, and then see what you think the different shapes will produce. So the power functions we have already seen. If I have an even power, then the x to power even will produce a parabola shape. Again, pardon my non-perfectly symmetric parabola functions, but I trust that you can abstract from my hand-drawn pictures to think that this is actually symmetric. If I have x to power odd, then I will have myself a snaky shape like this, and this will classify all of the power functions to the odd degree. We've already also seen what happens to the roots. The fractional powers are, of course, actually roots. So x to power 1 over n is the same as nth root of x. And we've also already experienced their shapes. If I have an even power, so x to power 1 over an even number, I will have half of the sideways parabola. If I have an odd number, then this entire snaky shape will actually get flipped, and I will have the full graph because I can raise negative numbers to the, I can take roots of odd power of negative numbers, so my graph will also exist in the negative where it does not for the even roots. For x to power negative n, if we rewrite that in a different format, the negative power is actually a reciprocal of that power. So this is 1 over x to power n. Notice the difference between the roots and the actual reciprocal of the power function here, right? With the roots, it's x that's raised to the fractional power. With the reciprocal, it's 1 over x to the integer power, okay? And we've already seen that with the resistance of the blood flow example. And here we will also have 2 different graphs depending on the parity of x. Of n. If n is even, then the graph will look like this. So this is x to power negative even number. And if we have an odd power, then the graph will look like this. So x to power negative odd would give us this graph. This characterizes all of these different functions and what they look like, and is a good sort of cheat sheet to have in case you want intuition on the graphs of these functions without having to call up Desmos. Let's take a look at more examples of the types of questions that we can ask regarding these different types of functions. Again, I encourage you to pause here and think about the answers to these questions yourselves before coming back for the answers. So the first question is, which of these functions increases most steeply for the values of n that are greater than 1? Okay, so greater than 1, notice that I have no coefficients here, means that we're talking past the switch point if it occurs. So for example, if we're thinking of x to power n around 1 or greater than 1, we're looking at x squared, x cubed, x to the 4th, and so on, higher and higher powers of x. How do they behave when x's grow larger and larger? For greater than 1, the highest power dominates, and therefore that will be the one that increases the fastest. Okay, so greater than 1 means I am looking at the higher power, which will dominate, and therefore will increase the fastest. Now, this is only really in regards to x to power n, but what about the other powers here? Well, if n is large, then 1 over n is going to be very small. If n is, let's say, 100, then 1 over 100 is a very teeny tiny number. whereas this one here will be 1 over x to 100, which again will decrease. We can also think about what the graph of that would look like for the 3 different types of functions, right? So let's say I have, once again, my scale-less graph here. So if I have the function x to the n, let's say we're looking for positive values of x because, of course, they're greater than 1, then I'm not actually concerned about what happens before that, whether it's a snaky part here or a parabola, it doesn't really matter. X to power n will look like this after the origin, right? What about the graph for x to power 1 over n? Well, according to the previous slide, x to power 1 over n will look like this. And again, sort of independent of what happens here. So they might continue in different directions. Either this will be a snaky part or it will not exist at all. And for the blue graph here, either it would be a parabola or it will continue off in the snaky direction down. It doesn't really matter. In the positive direction, their behavior will be fixed. Okay? And what about x to power negative n? Well, x to power negative n is the function that is actually decreasing throughout. So here I'm going to have something that looks like this. Let's make it go through the same switch point just to have some sort of symmetry, right? So this function is altogether decreasing. And for the largest increase, we're looking at the largest power overall, which will be given to us by x to power n function. So the answer here is x to power n. Which decreases for large values of n? Well, this is actually very handy that we drew this picture because we can immediately see that there's in fact only one function out of these 3 that decreases at all, and that is x to power negative n. So the only function that decreases is x to power negative n, and therefore it's by default the answer. Which of these functions are not defined at 0? So we notice that our root functions and our power functions, the first 2, certainly are defined at 0 and go through the origin. And this is also actually another really important thing to remember because people tend to forget that you can, in fact, take roots of 0. A square root or the nth root of 0 is just 0. So the roots are all defined at 0. The power functions are all defined at 0. They will also just be 0. But what happens here? Recall that x to power negative n is just 1 over x to the n, which means that if I plug in 0 for x, I end up with 0 on the bottom, which of course is not allowed. So the only function not defined at x equals 0 out of these 3 is this reciprocal function. Which functions are not defined for negative x values? So here we remember that there was a question about roots being defined or not defined for negative values, but not all roots, only even roots. So the only things that are not defined for negative numbers is x to power 1 over the even number. Even roots are not defined for even numbers, but the odd ones are. Now, let's compare the values of these functions for small values of n between 0 and x. So here we're talking about the near origin behavior. And again, we can call upon our graphic intuition to see what happens. Near origin, we suspect that the rule that we have had before would work here as well. Smaller powers dominate. And this is, of course, confirmed once again by our graphs here. We can also confirm it by plugging in various numbers. So pick a number between 0 and 1. Let's say 1/2. So we can plug in and see what happens. 1/2 to power, let's say, 3, 1/2 to power 1 over 3, and 1/2 to power minus 3. And then compare them against each other to see which one will be the largest, which one will be the smallest, to establish another kind of intuition based on numerical evidence. But you should confirm the fact that near the origin, the smaller power will dominate, and this is also consistent with our sketch in the fact that the smallest power, being x to power negative n, will be the largest. The next one will be x to power 1 over n, and the largest power will be the one trailing the furthest behind, near the origin because the small powers dominate here. Higher powers dominate for large numbers, small powers dominate for small numbers. That is the rule. That is something that will be consistent throughout. So all of the observations, the numerical and the graphical ones, should agree on that conclusion.